Yeah, thank you. And thanks for the kind introduction. And I want to start sharing just a few words about me. I am a trained theoretical chemist, moved to data science, and am currently working, like said, as a data scientist at Elio. We are a small consultancy dealing with all kinds of data science related problems, from building data platforms, which we heard a nice talk before, and implementing LLM use cases for clients, but also typical data science projects where it's all about decisions. And that's a specialty topic of mine, always advocating for making better decisions and giving tools for that. And one question I asked me some time ago is, I do all this stuff and complicated stuff at work, but do I practice this in my everyday life when I have to make decisions? And if not, why not? So to preface a little bit, what can be the typical data science problem we deal with in our jobs, and I think most of you have some impression of that, but this could be things like working with predictive maintenance, optimizing machines, doing recommendations, maybe book recommendations or film recommendations, or anomaly detections like in medicine, or for example also in cybersecurity, where we use our data to detect anomalies. And all these cases have something in common. Basically, we are trying to use the data to improve decision making. And at the end of all this fancy stuff we do with our data, most of the time there are decisions. And there are also decisions in our real life. So there are a wide range of decisions, and I try to come up with some differentiation between what those decisions could look like. First of all, there's a broad array of casual decisions, like, for example, when we're choosing to go to a new restaurant or a well-known one. That's an easy decision we do quite often without much thinking, and there isn't much downside as well with this decision. Maybe we have a bad meal, but that's it. And then there are those kinds of intermediate decisions where there are consequences, but not that heavy consequences. Like, for example, the poor guy here in the picture is learning for an exam, and he has to do maybe implicitly to decide how long he will learn for the exam, how much time he will allocate to learn, and this will affect how likely he will be to pass the exam. Or, for example, when you're preparing for a talk, you have to decide how much time you will use for your preparation. And the third category, I would argue, are the really, really big decisions. Here, the lady looks at a house, and maybe she decides buying it, and that are decisions you do not do very often. So there's a bigger downside, and yeah, this I would say is the most difficult kind of decision to make. Maybe also like to switch a job. There are huge consequences, and you have to consider very carefully. So if we compare these two kinds of decisions and we look with our data scientists' glasses on that, we can come up with several categories in which the data science, the work decisions may differ from our real life decisions. First of all, concerning data. In our job, we often have a great array of data, most of the time maybe even too much data, and we need to use our toolbox and data transformation to get high quality data, but most of the projects have some kind of data at the start. In real life, that's not really the case. There's only often a very little, if any, amount of data, but on the positive side, maybe we have some intuition about the decision we make. And it would be nice to consider this gut feeling. if we look at the decisions, often in the data science world, we do extensive training processes on our data sets and then put it to work and let the machine learning algorithm make decisions. And I would argue in the real life that's not the case. Yeah, we only have very few data. We may train ourselves a little on the data we have, and then we have to make a decision. And from this decision, we may get feedback whether it was good or bad, and then we can do our next decision, and we gather more online type data as we go. And I think the most important topic is resources. We solve the problem at work because someone pays us to solve them. And that is not the case in our real life, and we only have ourselves. At work, we have colleagues, we have great tools in the cloud, or we can reach out to experts and they use their time. And that is not the case for real-life decisions, and I think that makes a huge difference. And the fourth point I want to highlight is that in the business perspective, most of the decisions at the end boil down to money. The bottom line of the company, if the company is successful, the decisions might be good. And I would argue that we do not optimize our personal lives, at least I hope so, only for money. So there are much more metrics, maybe like happiness, maybe peace of mind, maybe friendships, all the stuff, health. We need to optimize our real life decisions, and that's quite a different regime. And all this comparison might explain that we do the one thing at work and not deal with the other kind of decisions. But I would argue it would be worthwhile to look at our real-life decisions and ask ourselves, as data people, can we improve there as well? And yeah, obviously, I would argue yes. Otherwise, we would be finished now, and we could have a very long Q&A session. Therefore, I want to show a small example about Bayesian inference and how we can put this tool in our data scientist toolbox to make decisions in this real-life type cases. So, just a few words about Bayes. The Reverend Thomas Bayes was a Scottish mathematician in the 18th century, and he developed formalism to work with probabilities, especially conditional probabilities. And the famous formula is here shown in the center, where you can transform conditional probabilities, so the probability that one thing happens conditioned on that another thing has already happened, into each other. And this gives us a great formalism to work also with data, where we can put together our intuition about some question and the observation, which is the data, and arrive at a combined estimate. So this is what is shown on the right, that we get a posterior distribution when we put together our prior intuition and a likelihood, which means how much fits the data to our prior intuition. And now the question is, why is this useful for real-life decisions? And to make this a little more clear, I want to show a small real-world example where this poor guy in the picture, there he is again, was me, and I had to prepare for a certification, an Azure certification, which is an exam you take if someone didn't have the pleasure yet to do something like this. It's basically like a driver's license test. You have a huge catalog of questions, you can train yourself on, and then you take the exam, and most of the questions in the exam are from this catalog you got somewhere. And the real life question is now obviously, when do I take the exam? Yeah, I have my test questions and the results I have in answering the test questions. That's my data, and I want to decide, have I learned enough? And yeah, normally, at least that was what I did in school. You do this with a guesstimate, and you think, yeah, it will be all right. But the question is now, can we improve this gut feeling with the data in a useful way? And is there something to learn in general from that? And to model a question like this, I took the PyMC package, which is a Python package to use for making Bayesian inferences. As a small disclaimer, for the small problem, it might be a little overkill here, but I want to show the workflow on a simple example, how one might use this tool. Here is some code for the modeling, and this basically contains all the logic we use. We define some prior distributions, our initial guess, and then the data comes in, and at the end we arrive at a posterior distribution which the PyMC package samples for us. For modeling my expected points in the test, I used a beta distribution, which is simply a distribution bound between 0 and 1. So it's perfect to model a fraction of something. And yeah, hopefully I arrive at a distribution like this, where some part of the distribution means it's equal to the probability I will pass the exam, and the red half I don't want to end in. So how did this all start? And this is the first step, the prior distribution, and for the problem here, I chose a really flat, uninformative prior. You see the probability distribution changes not very much in the space shown here, and it is simply a mixture of beta distributions. And I also highlighted the passing thresholds. When I learned, I thought the passing threshold was 80%, but at the end it was only 70%, so I shown both, and the numbers are the amount of the distribution that is below the threshold. And we see the initial estimate is that in over 60% of the cases, the exam will be failed. So one common concern when you talk about Bayesian methods is always, the priors, they induce so much subjectivity. And that's bad, because we are data people, we are facts people, we do not want to have any subjectivity in our work. And I would argue that's a little bit flawed, because if we use other methods, there are always assumptions we do in modeling. And oftentimes we are not really clear with ourselves what assumptions we make. And I think a framework where the assumptions are really, really clear and you have to define them from the start is much better to communicate with which assumptions we start. And now we made the assumptions, and now the data comes in. And basically the workflow is quite easy. First of all, I have to sit down and answer a test exam, like 20 or 30 questions in this case, and this took me approximately half an hour. Then I can gather all this data together, and here the Excel sheet was my friend, and then compile my own data set, and then I can update the posterior distribution. And the picture on the right shows how the distribution evolved with feeding more and more data. And there are basically two trends. first of all, the mean of the distribution moves to higher numbers, and second of all, the distribution becomes much more narrow, which means that my uncertainty is less and less. And I think this certainty measure is really important for making our decision, because we want to know if we take a huge leap with our decision, or we are quite sure that things will be fine. So, going now back to answering the initial question, we need this transformation back because we do not need really a probability distribution. The distribution is nice for modeling a problem, but at the end we want to answer a simple yes-no question. Do we take the exam or not? And therefore we must transform the distribution back to the simpler picture and calculate how much weight of the probability distribution is below a certain threshold. And if you've done the Bayesian modeling, this is quite easy because it's simply counting. You have your distribution, which is basically a huge array of data points, of likely results, and you just count them whether they are above or below a threshold, and that's really nice at the end to get to a simpler metric for decision. And that's another great strength of the Bayesian framework, that you can do statistic modeling of some quantities, and afterwards, when you have modeled your distribution, you can put out the points out of the distribution and do some algorithmic transformations on that. That can be very easy things like counting here, but it can be also very complicated logic. For example, when you think about election forecasts, where you have a seat distribution at the end, but you only model the percentages the parties will get, and the logic between this can be quite difficult when you need to calculate all this Überhangmandate. So I do not know the English term, at least the German listeners will know. And yes, that is very nice to have this method where you can have both parts. So, what did I learn from my self-experiment? First, I passed the certification with 90% of the points, so the prediction was pretty good. And more work was needed to do all this data gathering, especially the data gathering and the simulation, but it was a success. But what is much more important for me, I think, is what is in the second layer, that I learned a lot about practicing what you preach. And you think, when you have a problem and you think, yeah, that's not really suited for my data scientist toolbox, how can I work around this? What can I do anyway to, for example, inform a decision? And yeah, data collection can be very hard. I think that is an important topic to learn, especially as a data scientist, when most of the time you only come in when the data is already there. So thinking about actual data gathering and valuing the data you have is also a very important learning. And I think the Bayesian modeling can be a good method to inform other decisions. So, was it worth it? I would say, if it only was the one side, I would definitely say no. But I think the deeper learnings was worth the pain. And yeah, I want to highlight another takeaway about resources, that this might be quite a complicated framework, and you do not want to invest this for all of your everyday life decisions, because you do have finite time and this and too much decisions, and this is I think one of the main differences between our professional world and the private world. And therefore it is helpful if we can learn on a higher level about modeling some problems, and then improve our decision making in general. So I called it here intentionally over-engineer for some cases to learn the bigger picture a little bit more, maybe to change our own assumptions. In the case I presented here, it was, for example, that most of the time I learned too much, and the method showed me how I can use much fewer tries to be confident as well. And yeah, some real life decisions may justify all this work by itself. And a second takeaway I want to highlight is that the general Bayesian workflow can be quite a useful framework to think about decisions in general. That you define for yourself, or especially when you're communicating with others and have to make decisions together, what are your priors, what are your prior assumptions you base your decision on, and what would be the data to change your priors. And to have this in two and have this in two clear buckets and not mix it together. And that's, I think, very important, and we can all profit from that when we think about decisions. So I have to admit, maybe the poor guy at the desk was quite an easy example, and with real life decisions it might get more and more difficult the more important the decisions become. Like, for example, at the bottom, when you have to decide whether to change a job, move to a new city, or stay where you are, maybe with your work friends. But all of these problems share some characteristics. For example, complex metrics. We do not have often the real relevant data at hand at first, and often we have only one-shot decisions or very infrequent decisions, and we have immediate consequences, so that the decision on very low amounts of data have to be as best as possible. And this gets even harder the bigger the decisions are, especially when we think at high-level business decisions or decisions in politics. At least with my personal decisions, I have my own metrics, but when it comes to politics, everyone has its own metric, and that's a problem. But I want to end with with a claim that we, I think, desperately need better decisions for ourselves and for the society, and therefore we need to improve our decision-making toolbox. And for example, it is crucial to improve communication around decisions, and we as technical experts can do our share, and I would encourage all of you to help others and also yourself to make better decisions in the future.
All right, thank you very much, Tim. That was an amazing narrative. I would love to imagine you sitting there before taking the exam and like knowing exactly what's gonna happen. All right. On the other hand, we do have a few questions on Slido. So first of all, is it fine in your opinion to choose a prior based on little data or only on expert opinions?
I think both is fine is a big word, but I think both can be justified. When you choose your prior on some small amount of data, you basically have no prior and just do the first steps of your inference, I would argue. And that can be fine, for example, when you have a complicated model just to lower the computational demand. So I think both is fine, and it's important, but the most important thing, I think, is to communicate what you did and why you did it.
All right. Now a follow-up. How would you model the problem in your hard example, like a decision or accepting a job offer, moving to a new city, and so on, in this framework?
Yes, that's a really good question, and I think that that is a hard problem. But I think first of all you have to ask yourself, what is my metric for this problem? And that is, I think, much more difficult. For example, what you could do is use other people's decisions and look how likely they are on different metrics to yourself, and how good they valued their decision. The easiest thing is to talk to people who have the same career path, and then do some modeling. And I think you could gather data and could arrive at a model which could be very interesting, I guess.
All right. Last question, something that's also quite interesting to think about. How can you model forgetting something as time passes? And as an example, you might fail the test in a year, even though you might ace it today.
That's a really good question, because this concerns a slide I kicked out because of time. So I'm happy to answer a question like this, but I thought of it the other way around, as a time component, that in the simple model here, the assumption is that I do not get better with learning, which is kind of skewed, obviously, and you could use a time constraint, so that you kick out or weight points that are back in the future lower. And I also thought about, that was one exam. I could also take another exam. How could the data of the old exam transfer? Maybe that's kind of the same, like doing the same one in a year later. And I think then it would be justified to inform the prior with your previous data on some kind, and use this basically. But you do have to have some kind of data for your new prediction, I would argue, at least.
All right, thank you. Is there any more questions in the audience right now? If you don't have access to Slido, well then, let me actually take the stage and ask you. Okay, thank you. No worries. So you presented this narrative, and it's quite intriguing, and sounds a bit convenient, like one of those, I don't know, 90s or early 2000s movies where I have everything calculated. I know the exact odds of something. It's like 88% that it's going to be true. Anyhow, so is it just a narrative that you brought us today, or did you actually do this in some instance in your life?
I think the important stuff, and that's one thing I like about the Bayesian method, is that with all this modeling you have uncertainty, and that's really important. And I think that at the end, no one can make the decision for you. You can just inform your decision as best as possible. And I would totally say that there is no like objective way to make decisions, and therefore I think methods which incorporate these edge cases, this I can fail, I can lose a game, whatever, are preferable, especially in this real life cases. So yeah, that would be my answer to your concern.
Sounds like an amazing tool for my own anxiety. Anyhow, yeah, thank you again for listening, and thank you, Tim, for the amazing talk. That's it. Last talk of this panel.